To the end, I'm Casey Olson. My project is on using predictive modeling to classify human activities being things like sitting, walking, ascending stairs, and so forth through the use of wearable sensors and motion tracking cameras set up in a smart home environment. The data set I use is publicly available through a research group called IRC Sphere out of the UK, and their stated purpose is to develop home sensor technology for diagnosing and managing health and well-being. And for example, a clinician might use this technology to monitor an aging individual who might be living at home alone, and they'd be able to detect changes to their daily activities that they might find troublesome. A little bit about me. I'm from mechanical and biomedical engineering. I previously worked in medical device research. I've got professional interest in sensors and imaging and developing automated tools, which is what brought me to data science in this galvanized program. And I'm in Colorado because I love mountain sports. So to look at the raw data that I'll be using for my modeling, first of all, the wrist-worn accelerometer. It measures acceleration in 3 different dimensions, the X, Y, and Z axes, and you get a time series data like what's shown here in the lower left, where if someone's moving, then you get a change in signal from the movement. So here's an example of someone walking, but in contrast, if someone was standing or sitting still, you would expect a flat line. And on the right, these are the motion tracking cameras that are set up in this smart home environment. There's 3 of them in 3 separate rooms. And the data I get is when someone walks in front of it, they have automated software that detects a human walking in the frame, and it draws a green bounding box around the person. And the data that I have from that is a time series of the coordinates of that bounding box. So my goal is to take that raw data and create a machine learning pipeline, process that, featurize it, develop a learning model on it that will predict one of these 10 postures or actions on the right. So getting into that, the first thing I do with a time series data, in this case, I chose to break it up into windows. And I picked to break it up into windows between 0.5 and 2.5 seconds and evaluate maybe what an optimal window size was for predictive accuracy. And when I look at windows, I'll grab a section of data out of it like this. And in a 1-second window for the accelerometer, I get 20 data points as shown. And the simplest thing to do is just to kind of create statistical aggregates out of these data points. So I made a feature out of the average, another one out of the peak to peak range, and another one out of the standard deviation. And then looking at the bounding box imaging data, I made simple measurements on the bounding box in general, things like height, width, and centroid, and then did statistical aggregates of those measurements across each window. Ultimately, I ended up with 32 video features and 24 from the accelerometers that were input into a learning model. I found the best one that worked was a random forest classifier. And then on unseen test data, I evaluated it by seeing how accurately it did classify these 10 movements and postures. So looking at the accuracy of these models, first I trained one just on the accelerometer data just to kind of compare the difference. And you can see that the accuracy improved quite a bit as we increased the window size. And then when I added video data to the model, it jumped up quite a bit to 96%. So that was a big boost. And looking a little further into where our data misclassified, this is just like a small subset of some of the classifications that didn't work as well. You can see that turn, for example, a turn movement was only classified correctly 69% of the time. And 19% of the time, it was actually misclassified as walk. And you can probably understand that turn and walk might be similar. Someone would probably turn while they were walking. But to understand how the model determined between these 2 classifications, I looked at the important features, and it did this by the width feature from the bounding box. And you could imagine that if someone was walking past the frame, maybe the same profile would always be facing the camera, but if they turned, then at one point they'd have a side profile facing the camera and the width of the window would change. That's kind of my guess. And if we wanted to improve this model, we might think of a different way to distinguish between walk and turn that we could input as a feature to the model. But at the same time, we might think that we might have to keep in mind that this data was annotated by people. And it might be really hard for them to distinguish exactly the difference between a turn and a walk. So if they have a 19% error in distinguishing between the two, then that's as best as we're going to do. So in conclusion, this model performed really well, better than I expected. And I found out the video data is going to be very valuable in this kind of a setup. And I think it could be a really useful tool for non-invasive patient monitoring. And since I'm last, I want to thank the Galvanized staff. It's been a really memorable past 3 months, really challenging, but they've made it really engaging and fun. So props to all of you guys. And any questions?